Okay, so now you should see my presentation, I think. Anyway, so thank you everyone for being here today, and also thank you, Selma, for having me today. My name is Denis Angeletta, and I'm a junior software performance consultant for RETIT. And today I'll try to make reactive libraries a little more accessible, as well as share my experience evaluating the impact of such libraries on software performance. So more and more library providers release a reactive implementation of their product, and if you integrate a new library, reactive or not, that has to thoroughly be reviewed. So you ask yourself different questions. How much code is impacted with the new library? Does the complexity with the new library increase? What are the performance implications? How many developers in your team have to be involved in the change process? And what this presentation tries to do is essentially give you a rough idea on how much effort is necessary to integrate a new reactive library and what the performance implications are. The reactive libraries and/or frameworks used in the demonstration are on Quarkus, RESTEasy, Mutiny, Hibernate, a Postgres client, and obviously the Postgres database. Every single library here has a reactive implementation that can be mapped to a specific component inside a microservice architecture. And reactive libraries do not have to be used inside fully reactive environments, but there are some restrictions. That also means that for some implementations that it is possible to combine reactive libraries with non-reactive ones. And yeah, we will go over the possible combinations in later slides. Before going over the details of some examples for every component, let's start with the reactive mechanism that is at the core of the majority of our reactive libraries. So the core mechanism in reactive applications is known as I/O threads. Traditionally, Java Enterprise frameworks assign a thread per request, which obviously doesn't scale very well. In other words, you need multiple threads for concurrency. And that is because if one thread interacts with a remote source, that thread is blocked, and that also means that that thread cannot process another request, which obviously also limits the achievable concurrency. On the other side, the reactive thread mechanism relies on non-blocking I/O. That means that the same thread also can manage multiple requests. So when you communicate with a remote service, API, or database, instead of blocking a thread, an I/O operation would be scheduled and with a continuation attached to it. So for instance, you get a request, or if a request comes in, that retrieves an entity from the database. Instead of blocking, that request would schedule an I/O operation, and a continuation would be attached to it, which means then that other requests can start execution, or rather can start their processing on that I/O thread. So if we go over this display here, if request 1 comes in, it would start its execution on that I/O thread. Maybe there's some interaction with the database, then it starts scheduling that I/O operation, computation, whatever. Another request would come in, would be able to process on that same I/O thread until maybe request 1 would continue with its processing. So let us start sort of at the very top, and in this case, Quarkus. Quarkus is your typical framework that provides all the necessary tools to design and implement applications. And in this case, it has been chosen because next to its imperative stack, you also have the tools and libraries for implementing reactive applications. And in particular, in the beginning of this year, it started to provide support for new major releases of RESTEasy Reactive and Hibernate Reactive. Quarkus itself is also based on in a reactive framework called VertX, and that, or rather, because in Quarkus, if a request comes in, that request would first be handled on an IO thread, but then the processing work would be handed over to a second thread from a worker thread pool. That dispatch has an overhead that can be proportionally be big, but only if the underlying method in the controller does something as little as returning a string. But that mechanism can also provide, or can already provide, some improvements in combinations with non-reactive implementations that I go over in a little more detail in later slides. So the point of entry in your applications is usually where something like RESTEasy comes into action, and that is because RESTEasy is responsible for modeling your business domain as a resource, and you usually use something like HTTP over REST, maybe gRPC, that enables the communication with the underlying resource. And just in general, it checks an incoming request and provides the response that is appropriate to the outcome of your business transaction. So here we have a method, or rather, we have a method from an implementation of an API interface. That method is or represents a post request that first verifies the values from inside the request body, and in case of an error would throw an exception, and otherwise the underlying service method from the service layer is called. That is something you probably have seen before. There are no reactive components involved in this API method, so this is just in general your classic RESTEasy implementation, or you would use RESTEasy Classic. Now let's take a look at how RESTEasy Reactive compares to RESTEasy Classic. There are multiple ways of using RESTEasy Reactive, and here you can actually see one of them. The implementation can almost be identical to RESTEasy Classic, and that is because you can start utilizing RESTEasy Reactive by simply setting the ad blocking annotation. The ad blocking annotation, or rather when an API method with RESTEasy Reactive is implemented with that ad blocking annotation, then the processing of the request would be identical to RESTEasy Classic. So if we remember this dispatch mechanism I've mentioned before, where Quarkus will first handle its request on the IO thread and then dispatch it to a worker thread. For RESTEasy Reactive, instead of dispatching a worker thread, you would or that processing of the request would also happen on the IO thread. And if you have RESTEasy Reactive with that ad blocking annotation, you have the same thing as RESTEasy Classic, and that means that it starts on the IO thread, but there's actually a worker thread dispatched. So reactive endpoints also cannot have any blocking interaction, because otherwise an exception is thrown, and that is because IO threads aren't capable of handling any blocking or long-lasting operations. RESTEasy Reactive, obviously, because it's reactive, can make use of reactive programming libraries like Mutiny, or can maybe return completion stages. You might have heard of Java or Reactor, but because Quarkus is tightly integrated with Mutiny, I'll go over Mutiny in more detail. So Mutiny can affect a wide range of your code base, and that is because instead of having your typical sequential code, the majority of your code would then be stream-based. So no matter where you import a layer with Mutiny, as soon as you have that layer, everything that is based upon that has to be refactored to utilize the reactive streams. So in general, Mutiny is a reactive programming library that supports asynchronous programming with observable-like types, and that means that rather the library is event-driven, which means that you can express what you want to do upon a given event, usually something like a failure, success, completion, etc. It also only provides two types compared to other reactive libraries. We have a multi and a uni, which can handle any kind of asynchronous interaction. The uni type represents a stream of a single item or failure, while a multi can represent no value and potentially an infinite amount of values. And one core difference between Mutiny and something like RxJava is that RxJava, when you, let's say, call your reactive type, flowable, for example, and then check what is provided or what operations you have available, then you would get like a flat list of 100 different operations. With Mutiny, you would only get suggested these operations that make sense at that point. So if you just create something, you would get create from or something like that, and not, I don't know, map to or whatever. So let's take a look at an example from Mutiny's or RESTEasy Reactive, and in this case, we have an order that is wrapped inside a uni, or a method that returns an order wrapped inside a uni. That means that the stream either returns a single order or a failure. For failures, you usually would create an exception mapper. You can do that as well for reactive implementations, but what is also idiomatic to reactive programming is to transform the failures of the stream into a response that you want and push it further down the stream. Additionally, because Mutiny is push-based with lazy evaluation, the computation would only start if the consumer subscribes to the reactive stream. Let me drink real quick something. I'm sorry. So taking a look at the service layer, we'll compare a service method with and without Mutiny. So the version without Mutiny should be self-explanatory. You retrieve values sequentially from external services. You calculate the sum before creating and persisting the entity. You also catch an exception that might occur. And with Mutiny or reactive libraries in general, as I said, you rarely explicitly try to catch an exception. An error would implicitly be caught and be pushed down the stream as a failure event. The reactive version of that service method, the bottom one, first combines all the results of the external services concurrently before mapping them to a new object. And for that object, then a code block is invoked, which persists the order and flushes the entity manager. So if we refer back to RESTEasy Reactive, or rather how failures are managed in a reactive stream, if any type of error occurs, let's say for some reason the concurrent mapping of those results here is has an error, then if you go back to the endpoint or to the controller method, that would be caught by the onFailure call, and then that stream would transform that failure to a new exception. And for your data access object, you usually, or data access layer, usually have something like an entity manager injected. The result of that interaction with the entity manager is then returned as a result. In this case, we have one method that simply finds the corresponding entity by supplying the entity type and the entity ID. So you can easily utilize Mutiny at this layer by simply wrapping the findings of your entity manager inside a uni or a multi. Let's go further down the stack and take a look at the data mapper layer. Hibernate is your typical ORM framework, and in combination with your Datasource client, it empowers you to more easily write applications that have persistence in mind. In a reactive implementation, unfortunately, you do not use your typical JDBC client. You have a Vertex SQL client. Just keep that in mind for now. And just in general, again, the core functionality of Hibernate is simply to map your Java object to a relational data model. And to utilize Hibernate through an entity manager, you might inject something like an entity manager that, as I said, provides the necessary method to communicate with the underlying data store. In this case, we have a method that finds an entity through the injected entity manager and returns that value wrapped inside the uni. If you have a solution with RESTEasy Reactive and a blocking Hibernate like we have here, so we do not have Hibernate Reactive here, then you would have to set the add blocking annotation on the API method to make sure that the processing is dispatched to a worker thread, because otherwise an exception is thrown. Because if you go back to how Quarkus handles requests in reactive applications, then there can't be any long-lasting operation or blocking operation on an IO thread. So Hibernate Reactive provides two ways to inject a reactive session. One way is to inject a single Mutiny session, and the Mutiny session essentially provides the same ways of interacting with the underlying database as an entity manager. The only difference is that the results are wrapped inside either a uni or a multi. There are restrictions to using a single Mutiny session, and that is Hibernate reactive sessions cannot be shared between concurrent reactive streams. So if you for some reason have combined the results of different external services and you use you cannot use a single Hibernate reactive session. The other way of utilizing a reactive session is to inject a Mutiny session factory. There are multiple ways through that session factory to obtain a session, and one way is to call the with session method. The other would be maybe to call the with transaction method. There is also with stateless session and so on. We're going to take a little closer look at with session. Just in general, in with session, if you have a nested call, then the same session would be used. So there wouldn't be a new session created. So we've gone over pretty much like shown some minor examples of the different reactive libraries. Let's take a look at or go deeper into the actual software experiments and or case study. The REST service tested in these software experiments provides basic ordering capabilities that are somewhat typical in an e-commerce platform, and in particular these endpoints are available, but we're going to take a closer look at the HTTP post on orders, and this method out of all the available API method is the most complex one. It interacts with 6 external sources, while the rest of the API either changes a value from an entity or simply returns that entity. The experiment is orchestrated with Kubernetes, in which every container has resource limits defined. That the order service uses a minimum of 2 CPU cores and 2 GB of RAM and can utilize up to 4 CPU cores and 4 GB of RAM. The order service also is instrumented with the Java order instrumentation of OpenTelemetry. The instrumented order service through that Java agent provides telemetry data to a Jaeger backend that allows us to visualize and evaluate trace data. Because these libraries that we have used in the experiment, especially Hibernate Reactive and Mutiny, tracing isn't fully supported yet for those 2 libraries, at least for OpenTelemetry. So I'll be showing you a trace from Jaeger later. So every component, for load testing first, JMeter was used with an added plugin that provides additional thread groups. During a test run, the order service first is built, then a Docker image is pushed to a registry, and afterwards Kubernetes deploys the core containers of the application and follows that up with a Maven container that executes the JMeter project with the included test script. And obviously, before finishing the test execution, the results are archived for later use and the previously deployed containers are deleted. So now that we have roughly covered the application used in the software experiments, let's focus on the more details of the experiment. So performance testing in general allows us to compare the characteristics of multiple systems and or system configurations. It enables us to meet performance goals that we have set ourselves or that were set inside of service level agreements. So for performance tests to be representative, the real usage pattern of the application should be mimicked as close as possible inside of created test plans for a realistic workload. So a good metric to determine that workload is a customer conversion, or is the customer conversion rate. That is a key performance indicator that describes the amount of users who conduct a certain operation on the website, on your e-commerce website. That usually includes something like the user buying a product. And by knowing the conversion rate and the amount of users the site receives, the workload can be derived and be modeled as an arrival rate. And so with an average customer conversion rate of roughly 3% in the traffic of a randomly chosen website, e-commerce website, we derived something about 1,000 requests per minute as a workload, which obviously isn't very high, but that's also, we haven't modeled these performance tests after high-load tests or tests that would be more suitable for or to prepare for events such as Black Friday or Christmas shopping or Cyber Monday or whatever. And in this case study, obviously we have different test cases that have been created to try to mimic a workflow on an e-commerce website as close as possible. For one, we have the online shop order test case that simply consists of the user creating an order and after checking out, receiving the order information. That test case will receive the bulk of the arriving requests with 300 arrivals per minute. That means that use case is executed 300 times every minute. We have also the user rescinding an order as a use case with 50 arrivals per minute. And in contrast to the first use case, the user would rescind the order after creating it. There's also the changing payment information and with 50 arrivals per minute, and the creating orders with multiple items with 25 arrivals per minute. That also portray typical use cases in an e-commerce platform. Former simply changes the reference card in the created order, while the latter adds multiple items after the order creation. And lastly, the test case 5 describes the order creation with unwanted items, meaning that some of the added items will be removed. So I have gone over every library and framework used in the software experiments. And as I've mentioned, some reactive libraries can be used with non-reactive libraries. And also during the case study, the application has been refactored in several steps until it became fully reactive. So for each step, a performance test has been performed to see the impact of the reactive refactoring. All in all, we have 7 variations. The first one does not use any reactive component whatsoever, so it's the fully imperative solution. The second one uses RESTEasy Reactive, but with the ad blocking annotation. So that means it's essentially the same as RESTEasy Classic or the fully imperative solution. That is because ad blocking, as you might remember, forces the processing of the request to also be dispatched to a worker thread instead of just being on the IO thread. Variation number 3 uses Mutiny as a reactive library. Variation number 4 has RESTEasy Reactive with Mutiny, but with the ad blocking annotation. That is because of Hibernate Classic here. Variation 5 utilizes Hibernate Reactive Mutiny, but RESTEasy Classic. And variation 6 and 7, both are essentially fully reactive, but just to see what the impact of the annotation is, we have for one version the annotation set. So now let's transition to the probably most interesting part of this presentation and see how these variations have performed. So the test setup, as I said, was executed for all of the 7 implementation variants. And because we're taking a look at the response time, obviously lower values are better than higher values. So the fully imperative solution number 1, is or averages a response time of 50 milliseconds, while the variant with the blocking RESTEasy Reactive, solution number 2, has a mean response time of 49 milliseconds. And remember again, the processing of the request between the two is identical, but using RESTEasy Reactive with ad blocking seems to perform, even if it's slightly, but seems to perform better than RESTEasy Classic. There's another set of implementations in that regard that is equally comparable. A variant with RESTEasy Classic, Mutiny, and Hibernate Classic, variation number 3, the green one at the bottom, has a mean response time of 31 milliseconds. Replacing RESTEasy Classic with RESTEasy Reactive and the ad blocking annotation, variation number 4, the purple one, produces a mean response time of 30 milliseconds. The overall response time distribution seems to have a lower tendency for RESTEasy Reactive with the ad blocking annotation. The performance of every variant that utilizes Hibernate Reactive is almost identical, and if you compare the 3 solutions, 5, 6, and 7, they only present slight changes in the mean response time or the range of data. Additionally, every variant with Hibernate Reactive seems to be outperformed by its counterpart, where Hibernate Classic is the difference. So if we take a look at variation number 3 and 5, so the green one at the bottom and the light orange one here, variation number 3 has RESTEasy Classic with Mutiny and Hibernate Classic. Variation number 5 has as a difference Hibernate Reactive, and the one with Hibernate Classic has an average response time of 31 milliseconds, while the one with Hibernate Reactive has an average response time of 35 milliseconds. Mutiny also seems to give you a significant performance gain. If you look at the variation number 2, which is the top one here, and variation number 4, the one here, the only difference is with Mutiny. And if you compare the mean response time, if you use Mutiny, you have 31 milliseconds of an average response time. And if you do not use Mutiny, you have an average response time of 49 milliseconds. And you might ask yourself in this, what might be the reason that Hibernate Reactive in this case seems to impact the performance rather negatively. So the negative impact of Hibernate Reactive in a current environment most likely is caused by how the library obtains reactive sessions. A session again is obtained through the with session method, or was obtained through the with session method of a Mutiny session factory. The session is automatically associated with that current reactive stream if you call it first, and automatically closed after work has been done. And also, if a nested call to that occurs, that same session is used. Otherwise, a new session will be created. And doing a test run, obviously, this causes the performance tests to start and stop multiple sessions. And with the already low response time between 25 and 55 milliseconds, the overhead of managing multiple reactive sessions most likely impacts the performance rather negatively or unfavorably, at least. Using a single Mutiny session is possible, but in the current setup not functional. And that is because Mutiny combines reactive streams concurrently, while Hibernate reactive sessions must not be shared between concurrent reactive streams. And that is especially the case for the create order method, where the results of different external services are combined. Additionally, because the performance tests run concurrent thread groups, a single Mutiny session would not work as well. So this is from like a performance benchmark from a Quarkus podcast, in this case Quarkus podcast 68. And here they have compared a fully imperative solution with a fully reactive solution. And they have, in this case, they have a use case called multiple queries, which is, from what I read, the same thing as I did with the create order, but with a lot more statements. And as you can see, until like 20,000 requests per second, the difference between response time isn't that big. So you might ask yourself, okay, how often do I have this much of a workload? Does it really make sense then to make the switch to Hibernate Reactive? Well, even if the difference in response time isn't that big, if you remember how the reactive thread mechanism works, essentially you utilize less resources for this compared to how a fully imperative solution would do, which considering that nowadays all the applications are deployed in a cloud environment, and in cloud environment the costs are computed by how much resources you use, it would still be, you'd still get a gain by using Hibernate or reactive libraries in general. So one more thing, as I mentioned, because of these rather young libraries, especially Hibernate Reactive and Mutiny, unfortunately, they do not have support in OpenTelemetry yet. You do have support for more commonly used reactive libraries like RxJava, Reactor, RxNetty, and so on. RESTEasy Reactive is supported. And so just to give you an idea what this looks like and why it also was sort of difficult to figure out the performance problems with Hibernate Reactive, you can see here you can see pretty much nothing. You just have your initial create order call from RESTEasy Reactive, and that's pretty much it. You don't see any type of like reactive stream operation or your interaction with the database here. Okay, so making the switch to RESTEasy Reactive can be simple, especially if no reactive types are returned. And that also can give you a minor performance improvement already. Out of all reactive libraries that have been utilized in this case study, or just in general, if you utilize a reactive library, the hardest one to get used to is something like Mutiny, RxJava, or so on. But the performance gain with such library can be substantial, especially when you combine the results of multiple sources concurrently, as it was the case in the create order method. The transition to Hibernate Reactive, on the other hand, can be as challenging as compared to Mutiny, and that is because obviously Hibernate Reactive uses a reactive API like Mutiny. You can also utilize completion stages if you want to. But in this case, I'd suggest to minimize the work, or if you want to get started with a reactive library like Mutiny, or in general Hibernate Reactive, to minimize the work, I'd suggest you inject your Mutiny layer maybe on top of your already existing data access objects. So you obviously do not have to refactor all these data access objects, but to minimize the work even further, you could inject that Mutiny layer right behind or right above your service layer, so between your service layer and where you have your controller. And that way you only wrap the results of your service layer in a reactive type, and then you only have to refactor your controller methods. Yeah, so that's pretty much it. Thanks for listening again. If you have any questions regarding this topic, feel free to ask me now or send me an email later on. I'd said if you really want to learn more about reactive libraries in general, I suggest you go to the Quarkus podcast, and in this case, the podcast 68 and 69, where for one, you have the Hibernate Reactive developers talk about Hibernate Reactive, also the performance of Hibernate Reactive, and the podcast 69 just have like one of the three main developers of, I think, Mutiny talk about the performance of reactive libraries as well. So thank you, and I'll be happy to answer some questions.